And we are live.
Cool. Hello, everyone, and welcome to a new Code With Us session today. We have the Secret Network team with us, and we will go today in a workshop on privacy. We have Reuven, Tom, and Asaf, all software engineers at Enigma, and they will walk us through in how to build a secret voting app from A to Z. They'll start by writing a very simple voting app, and then they'll explain to you what are the several privacy-oriented design considerations. Today, we have the Secret Network with us, and we will go today in a workshop on privacy.
Okay.
Technical difficulties, I guess.
Yeah,
Seems Adriana disconnected.
Seems like she fell into a time loop.
Can I just start?
I would say so.
Okay.
Thank you.
Cool. Yeah.
Looking forward to it.
Thanks. Okay, so welcome everyone. Welcome to the workshop. We are the team. My name is Tom. I'm here with Reuven and Asaf. We are from Enigma, and we are going to talk today about privacy on distributed apps and about the secret network and secret contracts. So let me turn off the camera so everyone can see the presentation. Cool. Okay, so before we dive into technical things and the code itself, for those of you who aren't that familiar with the secret network and secret contracts, I will give a quick overview. Will take about 5 or 10 minutes, and then we'll dive into the more interesting things. So Secret Network is introducing privacy to the world of distributed apps. Sorry about that. I'll turn it off. That's it. So yeah, we know that to gain adoption and usability, we need privacy. Blockchains need privacy. We see it everywhere. If it's front-running resistance in DeFi applications, or if you want to monetize digital content of some sort that is stored on-chain, or even if you want to implement a game on-chain. So let's say we want to implement a game of poker. We can do that if all the hands are open, right? And if everyone can just know what cards everyone else have. So the existing tools that we have right now does not meet those needs. And we have workarounds for some, but we don't have a native solution we can rely on. So to achieve this goal of privacy, we introduce secret contracts, and we're going to talk about them in a bit. But first, let's introduce ourselves. As I said, my name is Tom. I'm here with Reuven and Asaf. We are software engineers at Enigma, which is a major contributor to the secret network. And we all think privacy is awesome. And actually, a cool thing to say is that all the things you're going to see today is actually it's live on mainnet, and you can actually utilize these tools. And unless I say otherwise, all is live and usable, and you can, after the workshop is over, you can hop in and start asking questions and start developing for our network, which is cool. So as I said, Secret Network is a blockchain that lets anyone perform computations on encrypted data. Think like, as it says, think Ethereum, smart contracts, but encrypted secret contracts. We bring privacy to the smart contracts. So a little bird's eye view on the Secret Network. This is the first layer 1 blockchain with private smart contracts, which we call secret contracts. It is built on top of Cosmos SDK, which is why we are here today. Each node runs every computation, even the private, the encrypted ones. And of course, we work on top of Tendermint consensus algorithm, goes without saying. The native coin of the Secret Network is Secret, SCRT. It's used for staking, governance, and all the usual stuff. The secret contracts are based on CosmWasm. So we actually collaborated for a while, and we created our own version of CosmWasm, which allows us to perform the private computations. The secret contracts are written in Rust and compiles to WebAssembly. And it utilizes a combination of secure enclaves, which we will touch in a second, and encryption protocols to achieve that privacy. So on a high level, how it works. Nodes perform computations inside something that is called Trusted Execution Environment, or T. For those of you who are not familiar, it means that when the node performs the computation, even the node itself can't really read the inputs and outputs and what is going on inside the trusted execution environment. So even the node itself can't see what's going in there and can't decrypt the data. So as you know, we have different nodes which are validating in the network, and each of the nodes have a special, let's call it a decryption key, which is stored inside this trusted execution environment. It's inside this enclave. When a new node joins the network, the existing nodes exchanges keys with this node and transfers, shares this decryption key with the new node. And once the new node gets this key, he can also join the consensus process and validate blocks as well. The user sends encrypted input, so only the user and the enclave can decrypt the data, and the user gets encrypted output. So only the user can decrypt this output. And the contracts are using the state of the blockchain, but they use it in an encrypted way. So we have encrypted state, which also, again, can be decrypted only inside the enclave. So we have this scheme of things, and this is like on a high level how it works. Let's talk a little bit about use cases. What can we build with the secret network and these secret contracts? So first of all, let's talk about other chains. We can bring privacy for other chains using IBC, for example, or when IBC is ready in the future. We are very excited for that. And another thing we did is building a bridge from Secret Network to Ethereum. So people can actually send Ethereum to the Secret Network and perform transactions and send this ETH and play around the Secret Network. So how it works is that users send their Ethereum to a smart contract on Ethereum side. Then as a secret contract on secret network side mints a token we call secret ETH. So secret ETH is actually, I'll talk about it in a minute, but this is very similar to ERC20 assets on Ethereum. So we have secret tokens as well. So the user can have these secret ETH after he sends them from Ethereum, and with these tokens, he can do basically everything he can do with a regular token or with a regular ERC20 on Ethereum side. Then after the users get done on the secret network side, users can burn their secret ETH and redeem their original ETH from the smart contract on Ethereum side. So it basically can act as a coin mixer or bring transactional privacy, and all of that is achieved with fraction of the price of the products that we have today. So this is very interesting, very exciting, and it's actually in testing phase, and it's going to be live in the next week or so. So this is pretty cool. Another thing we touched is privacy tokens. So we have a standard called SNP20, which is very similar to ERC20s, but with privacy. So SNP20 tokens are tokens that are private by default, because, as we said, the inputs are private, the outputs are private, and the state is private. So we achieve transactional privacy by default. Secret SCRT is actually the first mainnet implementation of the SNP20, and it is already live, and you can use it, and it is very cool. And actually, all the applications built on top of the secret network works with this token. So we create here some this private ecosystem that utilizes privacy, and this is very, very cool. Another thing we can build is a secret AMM. I guess we're all familiar with the concept of an AMM. Like we have Uniswap, which I'm sure all of you know. When we build an AMM on top of secret contracts, it is actually front-running resistant by default, because again, the inputs are encrypted. So this is very cool, and it opens the door for many other DeFi use cases and products, and again, utilizes this privacy ecosystem, and we can build very cool stuff around the DeFi world with this. And the final example I want to share with you are something we call secret vaults. So secret vaults is a way for you to store data inside a secret contract, and you can actually implement all sorts of interesting stuff with this, like data marketplaces. If you want to monetize some digital data, like, I don't know, imagine Spotify implemented on a secret network where only premium users can access certain songs, or what else. You can then share a decryption key with your users, and they can access your encrypted digital data. You can store private keys on chain and use them, and then you don't need to worry about storing your private keys anywhere else because they live on chain. You can even implement signing clients using this. You can store your private key again on chain and send unsigned data to the secret contract. The secret contract will sign the data for you and output the signed data. So it's very cool. And I actually put 2 links here for you. So the first one is a blog post we did with Ocean, which we're a partner with. And this post is talking about all sorts of use cases you can do with secret vaults, and so it is very interesting. And the second link is for the Ocean Data Economy Challenge, which is actually going on right now. So if you are interested in that kind of stuff, you can hop on those links. I will link this presentation later, so you can check this stuff out, and this is very exciting. Next on this session, I'm done with the boring stuff. Now we will dive into the code. We'll see, as Adriana said in the beginning, we will see how to make a voting app, a simple app from A to Z. We'll see how to write it, compile it, deploy it on chain, and then Asaf will show us how to build the UI around that. So, Ruben,
thanks, Tom. Thank you for doing all the introductory stuff and explaining what we're all about. Let me just share my screen real quick.
I would suggest we pause for a few minutes just to see if people have any questions or not until we move to the next stage of the workshop.
Yeah, sure.
Yeah.
Sorry, go ahead. Questions.
Can you guys see my screen and my mouse and everything?
Yeah, perfect. So we have over 30 people watching the workshop right now. So in case people have questions, please use the chat and ask the team whatever questions you might have regarding what they have presented so far. If not, we are just ready to move on to the next stage of the workshop.
While everyone is either typing or sitting there silently, I just want to say thanks to everyone who joined the stream and decided to tune into what we have to say. In my part of the presentation, as we said, I'm gonna explain how to write secret contracts. We're gonna start with our template example and move up to a simple contract, and we're going to show how to build it from scratch. I am going to be assuming some knowledge of some things, and I hope I'm not assuming too much about our audience, but I'm pretty sure that most of the code that we're going to be showing is going to be relatively simple. By all means, ask questions. Ask questions in the chat if you feel that there's something big I have skipped. But we're going to be seeing Rust code, and we're going to be seeing makefiles, and we're going to be seeing a bit of CLI magic. So I hope that's all going to be comprehensible. And I've been rambling for about a minute, and I don't see any questions, so I guess I can move on.
Yeah, apparently all clear so far.
Cool. So yeah, as we said, we're going to dive into some code. See, there's spoilers here. We're going to build a simple voting contract. As we said, we're going to show how to basically build a secret application. And in the end, we're going to build a front end for it that, you can actually build a website around and all that fun stuff. So first thing we need to understand is basically how contracts on the network behave, I guess, their full life cycle, as we call it here. The first step is obviously you need to have some code, and the contracts are going to be written as a regular Rust module, Rust library or crate for people that know the terminology. We are though going to be compiling it to a WASM blob. Now, to people that don't know, WASM is a simple runtime that was initially, it was a web thing, and now it's used all over the place. So we compile it to WASM, we optimize the binary and compress it, and then we have to store it on the network. Okay. Storing it is a transaction that we're going to perform, and from that transaction, we're going to receive a code ID. Once we have some code that's stored on the network, we can initialize many contracts from that same code. So that's going to be step 3 here. We're going to first have a transaction that stores the code. Then we're going to show how we can repeatedly initialize the contracts from the same code. And each one will be a separate entity with its own address and state and all that fun stuff. Once we have initialized a contract, we can either query it to receive information from it. Sorry about the phone call in the background. We can either query the contract and and get information that the contract chooses to expose to us, or we can execute functions on the contract. We're going to be calling those handles later on. Those allow us to send information to the contract that the contract can store. We can basically do all the rich stateful operations on the contract that actually manipulate the encrypted state. So every contract that we'll upload is going to have 3 main entry points to it, or 3 main parts to it. It's going to have its init function that allows us to give some input parameters to the contract. It can set some initial state based on those parameters. It can do whatever it wants. And after the init function gets executed on the contract that we've uploaded before, we can start actually using the contract. We receive its address in return, and we can just, it lives on the network for the rest of eternity. The second function we're going to see is the query function that receives query messages. It is only allowed to read the state and return answers to users. It's not allowed to modify the state. And then we have the handle function that is allowed to read and write from the state, and also can receive any sort of messages that we define and return messages appropriately. This is very much the usual CosmWasm environment and the CosmWasm way of doing things, if people here have some experience with that. But I hope it's just relatively intuitive to people that are seeing this for the first time. When we get to the code itself, you'll see these 4 files in front of you. We're mostly going to be focusing on contract.rs. librs is just a bit of boilerplate. Contract.rs will contain most of our interesting logic. Then message.rs and state.rs are just going to be smaller files that define the message formats and the storage formats that we were going to be using. In our example today, we're not even going to be writing anything in these files. I'm just going to remove them later, but you will see them in the templates, and it's a good basic convention to have. And just keep in mind that these contracts are normal Rust modules, so you can just divide up the code however you like, and this is just a convention that you'll be seeing working with these contracts. So first thing, before we jump into that, what we're going to do first is look at at our template example. Okay, I'm gonna just move. There you go. So I don't know if this is big enough for people, but for people that want to follow along, I recommend that you hop into this repository. This is sorry. This is not doing what I wanted to. Here we go. We're going to be working based off of this template at first, and I'm inviting you guys to follow along. You can just clone this, or like here in the README, there's instructions for basically generating a copy of it on your own. In my case, I already have a version of it, pre-configured here in my CLI. So this contract is going to be this. Sorry.
Can you share
Here in the ID
also in the chat?
the what? The link to it?
Yeah, the direct link.
Can you send it to the YouTube chat? I'll send it in the private chat.
Yeah, sure. There is a private and a comment. Just hand it over and I'll put it in the comments.
Cool. So
perfect.
This is it.
Thank you.
Cool. Yeah. So I've already cloned this for myself, and this is what we're looking at right here. It's like I'm just checking out the comments real quick. Yeah. Okay. I think the comments I'm seeing are like delayed because I'm. Oh well.
Yeah, people just asked for the repo link, and I have just shared it here.
Yeah, I guess there's some delay between the chat and the stream and stuff. So we're not going to be digging into this code too much right now. I do encourage people to dig into it and see all the little details themselves later. But what I do want to focus on, and I hope this is like visible enough for people, is that in this repository we have a bunch of pre-configured stuff. In the source directory, we're going to see these 4 files that I've discussed before. We're going to see the cargo toml file, which is our basically it's the project configuration. It's the Rust project configuration. Has a bunch of basic stuff here, and we have a make file that has that also has some useful pre-configured stuff in it. Yeah, cool. Now, this contract that we're looking at has this following behavior. It's basically a counter. It's a very, very simple contract that all it does is it maintains one number in its state, and it allows us to it just allows us to initialize the state with some number. It lets us find out what that number is, change the number, just increment it, and reset it if we want to, right? So in order to do that, we're going to be using these commands, these CLI commands. Now, yeah, I'm just going to set up a local environment. I'm going to show you guys how to do that, and we'll see that once we, I'm just going to show you that all this stuff works. If you guys go to this website here in Docker Hub that I'm going to share in the chat as well. One sec. Adriana, can you send this to the YouTube comments as well?
Yeah, sure.
Thank you. Again, for people following along, this is a Docker image that basically starts a local development environment. It's basically, we have a mainnet today and a testnet, but it's a lot easier to work with a local chain that has a bunch of pre-configured stuff, a chain that you can reset and just play around freely with. So this is what I'm going to be doing here. So I'm just going to copy the command that's in the README here. I'm going to, sorry, I'm kind of tripping over my own words. This is the project directory where I have copied the counter repository. I have another tab here with this same directory. So I'm just gonna run this command here, and you'll see soon after all these log messages, it's going to, there you go, start executing blocks in a local version of the chain. Now, normally our chain runs on SGX hardware and requires a bunch of configuration and a bunch of very, very special things. This is a simulated environment, so it's going to behave just like a real SGX environment, but it's going to be showing us a bunch of debug logs when the contracts are running. It doesn't require any special hardware, so I can just run it on my laptop. And here in the logs, you'll see that it pre-configures 4 addresses that we can use. Addresses named A, B, C, and D. And I'll be using these accounts later on in order to just use the CLI. Now, additionally, for people following the people that came here from the workshop link, then in the workshop notes, we asked people to basically copy paste this into their bash environment. Oh, sorry. For people working with in a Linux environment, this will basically let you more easily or more conveniently use the secret CLI that's running inside the Docker environment. So this saves you the need to install secret CLI, configure it to the Docker environment. It just uses the secret CLI that's inside the environment. So I'm just going to do that. And if I do secret CLI keys list, I can see these same 4 accounts that we've seen before. Now, if I've already run this before, but if I run make all in this repository, so here it doesn't do anything because I've already run it before. Oh, maybe it did. Oh well. We're gonna get this file in our directory. This is the contract.wasm file is the compiled binary from the code in the template, and contractwasm.gz is the compressed version of it. Now we want to upload this file so I can show you what we're doing with it. So I'm just gonna do that real quick. Secret CLI tx compute. I think it's store, right? Wasn't it done? Let's just give it a bunch of gas to run and ask the CLI to wait for us. Oh yeah, sorry. Here I use the the local path to this file. I forgot this secret CLI, because it's running in the Docker environment. We have to ask it to we have to tell it the path of this file inside the Docker environment. If we look at the command that we executed, we'll see that it maps the working directory from which we executed this command to this path inside the Docker environment. So if I add this here, code, is it? Yeah. There you go. So now we've uploaded this contract that we've compiled from the code in the template, and we see that its code ID, as we described in the slides, we said that we will be compiling the contract and storing it to get a code ID, right? So once we've uploaded it, we can see the CLI tells us the code ID is 1. That makes sense, right? If I do this again, we're going to get code ID 2. But we're going to use code ID 1 for now. Now we're going to want to instantiate this contract. So we're going to have to run this command up here. Just going to have like a version that I can like copy paste here. Sorry about that. Cool. So we said our code ID is going to be 1, right? We have to give this a label. It's not very important. Let's call it counter. And we're going to use these same parameters from here. Oh, sorry. There we go. Cool. So we, in this example, we take these initialization parameters, right? We tell the contract its initial count is going to be 42. And we just send this message to the contract. It then parses this message and saves this to its state. And in the response, we can see this is the address of the generated contract, right? If we take this and save it to the side real quick, we're going to be using this to show how we can query it. Excuse me. Right, so if I then query the contract, we can see that the count is indeed 42. Now, the interesting part here is if we look at the contract state, we're never going to see 42 because everything's encrypted, right? This is information that's only available through, like you can only get this information if you directly query the contract. If the contract wanted to save something else in its state, we wouldn't be able to see this information. And we're going to be using this property later. Now, if we want to increment it, for example, sorry. Excuse me. There we go. If you go ahead and ask the contract to increment the counter, what did I do wrong? Oh yeah, I have a typo here. And then we query the state again. We can see that the count indeed increased. Right. So this is the basic CLI interaction with these contracts. Now, the application that we're going to be building today, as we said, is going to be a poll, basically. So what we're gonna do here today is we're gonna build a contract that manages one single poll, right? One set of votes. Every time we want to start a new vote, we'll instantiate that same code that we upload. We're gonna let people vote. We're gonna make sure that there's no way to find out who voted for what. And we're gonna make sure that people can't vote twice. Yeah, sorry. We're gonna make sure people can't vote twice. We're gonna make sure people can only vote up to a certain point. And importantly, we're gonna make sure that no one can see how the vote is doing until the vote is actually complete, right? So we're gonna make sure, we're just gonna be using the natural properties of our network where you can't see the inputs people are giving to the contract. You can't see the outputs from the contract unless you're, permitted to, unless the contract gives you permission to see something, you're not going to be able to see it. And since the state is encrypted, everything we save in the state is going to be hidden from the world. So, yeah. What we're going to do is I'm going to stop this local environment here for now. I just want to, like here in this folder, I just want to save this for now. So I'm just going to create a copy of it, of this counter project. Cool. Awesome. Just going to restart this chain with a fresh state. Right. Excuse me. Cool. C-Line has gotten really annoying lately for some reason.
You can always switch to VS Code.
Yeah, of course. Cool. Now, please bear with me for a minute. Just setting up some stuff. Cool. Now, this is a Code With Us workshop, but coding all of this by hand is going to be very slow for me. So I'm just going to do my best to explain what we're seeing. And I am going to be using some snippets of code that I've prepared in advance. But I hope everything that I show here will be, relatively easy to understand. If we look at the contract.rs file in the secret template, right, this file here, we'll see the three entry point functions that we've discussed. We have the initialization function, we have the handle function that lets us modify the state, and we have the query function. These other functions here are helper functions for the functionality of the counter, right? You can see the increment functionality here, the reset functionality here, the specific query functionality here. For now, I'm going to remove these because I don't need these for the voting contract that we're going to be building. Just going to delete these. There we go. And reopen. There we go. Should I explain basic Rust to people here today, or are people comfortable with me moving ahead and pretending like stuff is relatively easy to understand?
Do we have time for this?
I don't think so. So I'm just gonna probably move ahead. Yeah. So what we have here, we have a bunch of imports in the beginning. These FNs are short for functions, so these are function declarations, right? These are some generic arguments. You can ignore these for now. And we have the function arguments, the return type, and then the body of the function, So for the voting contract, we're gonna want to first define the initialization message, right? What kind of parameters we want to get from whoever initializes it. I'm gonna quickly copy over the imports that I'm gonna need. Cool. For initialization, we are going to want two things. We're going to want the name of the poll, right? So this is just going to be a random string that people can decide on. And we're going to want a deadline for the votes to come in, right? We're not going to be accepting votes that come later than some block height on the network, on the chain. Our init function is going to be getting a message, which is an instance of this type, right? There's a bunch of boilerplate, basically, that you're not seeing that parses the JSONs that we've seen on the CLI. That parses the JSONs into this type. So if you're sending a message to the contract that does not adhere to this format, it's going to be rejected before it even reaches this init function. Then what we're going to do in our initialization is, there we go. Again, this is like me copy pasting ready-made code, but hopefully this is simple enough to understand. We're going to want to access our storage, right? We're going to want to set up a few basic parameters. We're going to save the name of our poll, right? We're going to take message.poll, which is this information we got from users. We're going to store it to this location in the storage. Okay. Similarly, we're going to take the deadline that people have set. This section means like if people did not provide a deadline, we're just going to say it's like, some very large number. So we're probably never going to hit the deadline, so people can keep voting. And then we're going to store this deadline to this location in our storage, right? Similarly, we're going to set this variable running to true. I'm going to use this later. I'll explain what for. And then we're going to want to save some sort of tally into the state. Now, here, tally is going to be excuse me. It's going to be something that looks like this. It's going to be some type that has just two numerical fields, yes and no. Using this, we're going to we're going to save this thing to state. And this is what we're going to be using to count how many votes for something or against something were submitted over the lifetime of this specific contract, right? And again, we're going to, in our initialization function, we're going to say that initially there are no votes for or against anything, and we're going to save it to our storage. On top of that, and the last thing we're going to do is we're going to see who sent the initialization message. The message sender, as you're probably familiar with from Ethereum and other runtimes like that. And we're going to save it to this place in our storage. Okay. Now, there's one thing I didn't show here. Sorry. This function serialize, and this function serialize is actually not from our imports. It's a small helper function that I have prepared here. Just gonna copy it for now. It's not very important to understand what's going on, but basically, just gonna paste it here near the end. We're gonna be using an algorithm called bincode2 for serializing things into storage instead of JSON. The idea being that bincode2 is a binary format, and we want to make sure that stuff that we save in our storage doesn't, the size of things we put in our storage doesn't change based on the value of the things. In JSON, like if we were to save the tally as JSON, then it will probably look something like this, right? Like yes, some number, and no, then some number, right? But that means that the complete size of this message that we'll put in the storage is going to be changing based on the size of this number, right? And that can help expose stuff about people's votes. So using a binary format instead of a JSON format, we can basically help mitigate some side channel attacks. So this is like what you're seeing here, and like you can just ignore this for now. If you're the sort of person that is going to be very curious about this, then you can find us on the forums and we'll elaborate more about how this works. But for now, just we're going to be using this to put stuff into storage. Now, if we compile this contract and upload it at this point, we're going to be able to initialize it. But we want to define, how, what kind of information people can ask about this contract, right? So because this is a secret voting contract, of course, people will be interested to know about the tally. How many votes were cast for something or against something. But we also don't want to let people know what the tally was before, before the contract finishes running. So what we're going to do is just going to copy a big section of code real quick. We're going to allow people, so this is the definition of the types of messages people can send for queries, all right? One of the types that we're, the interesting type that we're going to talk about is getting the tally of how many, getting the tally of the votes so far. But something we want to make sure is that if the poll is still running, and here we're accessing the storage, right? If you remember in the init function, we set running to true in the state. So here we're gonna want to make sure that only as long as the poll has already finished, people are able to find out what the tally is. So if the poll is still running, we're going to be telling them that, we're not going to be exposing how many tallies have been, how many votes have been counted so far. But once we finish the poll, and we're going to be setting this value to false in a bit, then we will access the storage and access the tally in the storage, deserialize it. And here in this line, we're going to be returning it to whoever sent the query. Okay. So basically, this section here is going to be making sure that this information is going to stay hidden as long as we want it to be hidden. Right. Like if you just access the storage directly, you're going to see a bunch of encrypted garbage, and if you want to actually see information, it's only going to be available under certain conditions. The second the second option that you're seeing here is basically allowing us to fetch the name of the poll. It's like this is not very important. It's a little convenience that we added. You'll see it used later in the front end section. But the second type of query is just, given an address, we want to know what is the name of this poll. Now, we've seen how we can initialize the contract, how we can ask the contract what's going on with it. Now we want to be able to change things in the contract, right? So what kind of things do we want to do with the contract? We want to either vote or let the admin of the vote close the poll so people can find out, what votes have been cast so far. So this is going to be represented by this type, where we have two options. We either vote for or against something, right? Or we try to close the vote. And the way we're going to do this is going to be with this. This is going to be the biggest piece of copy paste, I swear, with this piece of code. That's it. Where, again, this is our handle function. And in this section of the code, we're going to be checking what the message was and actually acting on it. So if someone does want, we're going to get back to this section in a bit. If the message that a person sent was to vote, for or against something, right? We're going to first check if the person has voted before. Now, how do we do this? There's like a bit of magic here that, again, like I don't have enough time to fully explain. But basically, we're going to a new section of the storage called voters, right? Under this section, we're going to be taking the address of whoever sent the vote in. We're going to be checking if under voters/sender address, there has been, like, anything has been stored. If nothing has been stored, then we'll put something in there, this X thing. But if we see that something has been stored in there, then we're going to say, okay, you've already voted. I hope this sort of makes sense, but like basically you are able to pass this section only once with your vote. Like you can only, if you're voting from some address, then first time around, we're gonna remember that you voted. Second time around, we're gonna see, oh, you voted before, and we're gonna stop you from doing anything else. We're gonna say, sorry, you've already committed your vote, and we're not letting you do this again. Now, if we do see that it's the first time you voted, what we're gonna do is, in this line, we're gonna fetch the current tally of votes. Based on your vote, again, this yes argument, this yes variable is coming from here, which eventually comes from the message that the user sent. Excuse me. If the user voted for whatever this poll is about, we're gonna increment the count of votes for. Otherwise, we're gonna increment the count of votes against this poll, and then finally take the tally after modifying it, serialize it, and save it back into storage. This whole thing is happening inside, again, like this whole thing is happening inside the trusted execution environment. So no one from the outside can see what we're pulling from storage. No one can see which of these two branches we took, or what the contents of the message was. And like no one can see what we're putting back in storage. Okay. Now, yeah, so this is like the first type of thing we can do. Like we can cast a vote, and we can only do it once. Second thing we can do is we might want to close the vote, right? Like the administrator for this poll, whoever started it, might say, okay, enough time has passed. I want to prevent people from voting again. And we want to prevent people from voting again, and just let people find out what the current tally of the votes is. So if we get a message to close the poll, we first check if whoever sent the message is the administrator of the poll, right? If you remember in the init function, we took the message sender, said this is the admin, and we save it to the admin field in our storage. Now, when someone asks us to close the poll, we're like, okay, who was the admin? Are you, the message sender, the admin? If no, then of course we don't allow this. We say only the admin can close the vote. But if it is the admin, then we go back to this key that we mentioned earlier, and we set it to false, right? Again, where is this relevant? In the query, when we want to get the tally, we check, okay, is the contract still running? And give an answer based on this information. Cool. And the last part, the last part of this voting contract is going to be this section here. As we talked about, we might want to say that we only allow votes to happen until some deadline, right? So this section handles that. When a message comes in, we check if what the deadline was. We check the current block height compared to the deadline. We also check again, like, is the poll running still? And if we see that any of these conditions has been met, then we don't even check what the message was. We just always return the same error. We say, sorry, the poll is closed and you can't do anything else with it. I'm gonna check the comment section real quick. The trust is these only from Okay.
Do you see the comments?
Yeah, I'm seeing the comments. Are there any questions about what I've been talking about so far? I don't think so. I see people asking about secret tokens, but that's not what this thing is about.
Yeah, we will
Okay.
answer questions in the chat.
Yeah, thanks, Tom. Okay, so now that we have all these pieces in place, we have a contract that lets us, lets us name it, lets us set some sort of deadline for votes to come in until. We have a hidden state, which is the tally, which we only expose under certain conditions. And we have some basic permission system where we have one special address that is like the only entity permitted to perform some of the actions in this contract. Of course, you can take these principles and make them as complex as you want, because this is just, this is simple Rust code. You can expand on this however much you like. You can basically do whatever you want with these principles. So I'm just gonna show you quickly how we can compile this, upload an instance of it. I'm just gonna quickly show you how we can play around with the contract, and then we're gonna move on to Asaf, so he can show you how to build a front-end application based on this. So if we make all here, and this is gonna take this is gonna take about a minute. It's gonna build all the code that we've put here so far. I should. It's fine. Let's see. Oh yeah, sorry. I've mentioned bin code here before. I forgot to actually add it to our dependencies. Excuse me. I'm just gonna. My mouse is acting up. Okay. If we go to the cargo toml, I just need to add this one line here in the end. And while we're at it, I'm gonna remove these two files because we're not using them in the example, and I want this to compile faster. This is like a bunch of boilerplate that's not relevant right now. And bear with me for a minute. Oof, yeah. Compiling Rust is a little intensive sometimes. Cool. So now if we look at our current directory, we'll see that we have a brand new CosmWasm file. So we're going to again, we're going to connect to our local environment. We're going to CLI tx compute store root code track.wasm.gz from account A. We'll give this 1,000,000 gas just to make sure it runs. And we're going to ask this to wait until the transaction completes. Cool. So now we have this contract uploaded. We're going to, sorry. Instantiate contract one, like code 1. We're gonna give it parameters. And again, if we look at our code, the message we're expecting for the initialization parameters is gonna be looking like this. It's gonna be the name of the poll with some string and an optional deadline, right? So we can say the poll name is example poll, and that the deadline is some future time. Okay. Oh yeah, sorry. Need to add one more flag here. Cool. Every contract that you instantiate on the secret network has a label attached to it, which is like, it can be a human readable name. It can be just like some random thing, but you can later you can use this to reference the contract more easily later. We're not going to be using this now, but a lot of UIs might be using the labels of contracts. In any case, now we have the contract address. So we're gonna try to count the tally for now. Gonna query the state of this contract. We're gonna ask it to give us the tally. Again, this message is based on this, what was it? Here we go. It's based on this option, this enum variant is the terminology that we've defined before. So get tally, if we send it, it's gonna run this code here. If we do that, sorry, don't need all of these flags. It's gonna see, it's gonna tell us, there you go, there's no tally yet. Now, if we try to, vote from one of the accounts, say from account B, gonna tx compute execute from B, and we're gonna vote yes. Say we're gonna vote for this, right? Cool. So like the vote has been submitted successfully. If we query it now, we're still gonna see that the tally is hidden from us. But if instead we use account A, let's try this with account B first. Like if we try to close the poll with account B, it's going to, oh yeah, the answer is encrypted, but it gives us the transaction hash. So we can secret CLI. Yeah, okay. Secret CLI Q compute TX this. Oh, the message was, oh yeah, sorry. The format of the message was wrong, and you see the contract told us this, but only using this this CLI that has accounts A, B, and C configured, we were able to see this. Other accounts won't be able to see the error message. So if we try to use B to close this, and then check the error message, you're going to see only the admin can close the vote. Now, if we run this same close operation using account A, see it has succeeded. There's no error message to this. And if we query the tally again, we're going to see now that it has been exposed to us. We can see that someone has voted yes. If we try to vote again, though, we are going to, again, get some error. And if we look at the error message, it's going to be that same error message that we have configured before. The poll is closed. Cool. So this is the contract, and I'm going to hand this off to Asaf. It's going to show us how to build a UI based on this. I'm going to push the code that we've built so far. I'm going to push the code we've built so far to a repository so he can pick up the work. And Asaf, you can start explaining your stuff in the meantime.
Thank you, Reuven. Let me quickly set up my environment. Whoa. Okay. So I have here the contract that Reuven just built.
Oh yeah, you're gonna work off. Yeah, okay, cool.
And let's quickly compile it. So make. Okay, cool. Then let's run a local blockchain. What does it say? Start local chain. Start local chain. Whoa. Docker. Already have one with this name. Okay.
Just to explain, I didn't show this, but the version Asaf is working on is like an almost identical version to the contract that we were just working off of. It just has this make file. So the command I used earlier to start the chain is a make rule in this case. So that's that's everything that's happening there.
Yeah, I also have this command to store the contract. So let's run it. But first, just let me make this terminal read-only so I won't accidentally kill it. Make store contract. And we got it with code ID number 1. Now, what we are going to do is we're going to build a simple React app so that user would be able to create polls and vote using a graphical user interface. And also we are going to see how to integrate with Kepler wallet. So let's create a vanilla React app. Create React app. Let's call it UI. Probably gonna take a minute. Oh, maybe less. Maybe more. Okay. So now if we head over to the UI directory and run yarn start, this will start a local development server. that is going to compile the React app every time we make a change. And let's see it right now. Cool. Okay, the next thing I want is to, just a second, is to use the debugger for Home extension, so I will be able to set up breakpoints. So let's do this. Just a second. Port 3000. Web root is UI, right? And we have a brand new browser, and we're able to set breakpoints. Now let's head over to GitHub, Enigma. And what we have here is a template for working with ReactJS and Kepler. So we are going to use this as a baseline. I'm going to copy this over to our workspace, and then we are going to go over this really quick. So just copying this entire file into source app.js.
Should we share this link to the template thing?
Yeah.
I think we should also share the link to the repository that has a. Oh my god! I think we should share the link to the simple secret vote repository, maybe in the end of the session also, so people can see
sure.
all the code themselves.
Yeah, for sure. Okay, so let's go over this template real quick. We're going to use React and SecretJS. This is the name of our local blockchain for development. What this template does is it connects to Kepler, and then it pulls the main account balance from the chain, and it just prints it to the screen. So this is the constructor of our entire app, and this function is called once the app mounts to the screen. So the first thing that's going on is set up Kepler. Kepler is the wallet we are going to use, and I'm going to show it in a bit. So in here, we're waiting for Kepler to inject its object to the web page. And then what this entire code block does is it informs Kepler on the local blockchain we have. So it will be able to connect to it. Then Kepler prompts the user to allow Kepler to access the web page. And then we're going to set SecretJS using the offline signer that Kepler has. So every time we want to sign a transaction, Kepler will prompt the user to ask for permission. After all of this is done, we're going to update the internal state of the app that Kepler is ready, and the account, the main account that Kepler is using. Just a quick note for anyone that doesn't know React. So each component has an internal state, and every time the function setState is called, the render functions re-renders the screen. So if we go back to the constructor, we can see that the Kepler ready flag is false, and the render function will just print to the screen waiting for Kepler wallet integration. Failed to compile, can resolve SecretJS. So let's install SecretJS. cdui yarn add SecretJS. Okay, cool. Let's hit refresh. What is going on? Okay. Let's restart the development server. Why does it take so long? Okay, waiting for Kepler wallet integration. So this is this line. Now Kepler isn't ready because we need to install Kepler wallet. So let's install Kepler wallet for Chrome. And now we have Kepler installed. Let's hit refresh. And this is, we're seeing Kepler asking the user to allow for connecting for the local chain. So let's approve. And this is Kepler asking the user for permission to access the web page. Also, let's approve. And still, what is going on? Oh. So once we install Kepler, we need to create a new account, or in our case, we are going to import one of the Genesis accounts that Owen also used. Let's use account A. Import existing account name A, password 1 through 8, of course. And we're all set. Cool. Let's go in the Kepler UI to the local blockchain we have and see that we are loaded. Now let's hit refresh. And we can see that now the web page can access Kepler and pull out the main account and also the balance. Now let's go over what we want to build. I was thinking of maybe in here maybe put in a little form to create new polls. Just maybe an input bar and a submit button. And then under it, maybe just list every poll we have, and then maybe for each poll, be able to vote yes or no. So let's start by creating the form to create new poll. Okay, so this code, now that we hear Kepler is ready, and that is what we are seeing, account and address and the balance here. So let's quickly center this. And let's create the form for new polls. Header. Create new poll. Let's see that this is working. Cool. Okay. Now let's do an input field and then a button. Submit. Okay. Looking good.
Looks production.
Production ready, yeah. Okay, now on the input field, let's do on change. So what we want to do is, once this button is pressed, we want to get the value that the user typed in the input field. So we are going to create a new field in the internal state. Let's call it new poll text, and let's initialize it to an empty string. And then in the input field, we're going to set the value to be this state new poll text, and on change, every time a user inputs a new character, we're going to update the internal state. On change, and let's see if I remember how to do this. Target, event, and then this nekuda set state, new poll text, event dot target dot value, I think. Let's put a breakpoint in here and see. Okay, event target value A. Cool. And then B. Okay, cool. This is working. And now on the submit button on click, let's take this value and instantiate a new contract, just like Ruben did on the command line, but using SecretJS. So on click, const. I'm using await, so I need async here. So this SecretJS. Now we need to instantiate, right? Our code ID is 1. The init message will go, let's see what the init message look like. So init message is a struct, and we have a mandatory field that is a string, and then a deadline, which is optional. And so let's ignore it for now. Oops. So poll, and then this is the value. And I think we have another mandatory argument, label. So we don't really care about labels right now, so let's just do a random number. Because labels are unique across the chain, so we can just put something constant. Math, but random. This will look ugly, but you get the point. And okay, and then let's just print to the console and see if this worked. So should I eat a big breakfast?
You're asking the real questions here.
Yeah. Important questions. So we did invoke the instantiate function, which means we're sending a transaction to the chain. And Kepler prompts us to approve this transaction. So let's see what we got. Yep, this is what we inputted, and this is the transaction. This is how the message looks like after it is encrypted. Let's approve this. Okay, seems to work, I think. Yep, okay. And probably should delete this after. So this set state uphold text. Let's reset this. Okay, so this seems to work. What next? So now let's just list over here every contract we have, which means every poll we have, and see if we really get the new poll we just created. So let's just do another header, list of polls. Okay, so we need to get the list of every contract on the chain. Luckily, we have a function that can give us every contract with the same code ID. So I think we'll do this as a internal state field. So let's just call it polls. And init it as an empty array. Why does it keep popping? So let's do this ugly at first. Every few seconds, let's just get the entire list. So set interval every 1 second. So sorry, this at SecretJS get contracts, yep, by code ID. So const contracts, and we need to wait. Let's see if this is working. Okay, seems to work. Yep, and what we got is the address of the first contract we instantiated, creator, which is us, code ID number 1, and label, probably the random number. And we put there. Okay, so now what we need to do is go over, iterate on this list and get the poll. I think Reuven went over it. Yep, we have a query called get poll, and it just returns the poll text. So for each contract.
Yeah, just remember the messages are in camel case. Are not in camel case, are in snake case, right? Like in the code, they show up as camel
Yeah,
case,
right.
but we modified them. There you go.
Yeah, thank you, Reuven. I would
Just save you a headache if you were gonna.
Yeah, thank you. Okay, so for each contract, await this SecretJS query, smart, of course, and the address is c.address, and the query is, so this is an enum, and then we need the get poll, which is a snake case. So get poll like this, and that's it. Const poll, and then let's just add the poll as a field to the contract, and at the end this set state. How did we call it? Polls. Just the list of contracts. This should work. Sorry, this is poll. This should work, yeah. Let's put a breakpoint and see if this worked. Oh no. Okay. Contracts. Yep, this is the new field we just added. Should I eat a big breakfast? Okay, now we can use this state polls to list every poll on the web page. So let's just do this state polls. Now, each poll we are going to let's just return a div. And inside the poll text, p.poll, right? Let's, cool. Okay, so now let's try adding a new poll and see if it automatically updates here. So should I eat a banana for dinner? Let's see what we'll sign here. Okay. Okay, seems to work.
Woo! It's alive.
Yeah. Now for each poll, let's add a button for voting yes and a button for voting no. So how are we going to do this? Okay. Button and another button. Yes. No. Let's see if this worked. Okay. Cool. Now for each button, let's add an on click. And let's fill them. Let's do them ASIC. Probably gonna need it. Okay, so if I clicked yes, and let's vote yes. So this SecretJS dot execute. So the contract we are voting on is p dot address, and the message, let's see how the voting message looks like. It is also an enum and then vote and yes, which is a boolean. Okay. So vote yes, true, right? Okay. Const res await, and then let's just print res. The same thing for no, just with false. I know it's ugly, but we can refactor later. This is essentially the same function. And let's also, because I'm paranoid, wrap this with a try and catch. Console error E. Okay. What did I do? No address of null. Should I eat a big breakfast? Let's vote yes, but first, each child in a list should have a unique key propriet. React is annoying a bit. It says that this div is part of a list of divs because we are using map here. So he wants us to give it a unique key. So the unique key will be the index in the list of polls. Okay, cool. So let's vote yes. Actually, let's vote no on the big breakfast. Let's see. Vote no. And it seemed to
The
vote
yes true and yes false is so confusing. But,
true.
yeah.
Let's try to vote again. This time, yes. Yes. And we got an error. This account has already voted, and I think this is one of the error messages that Reuven wrote. Yep. Okay, cool. Let's try to vote no again. And again, this account has already voted. Okay, cool. So now what should I vote on the banana for dinner poll?
No.
No. Okay. Very strict. Let's approve this transaction.
Cool.
Cool, it seems to be working, yeah. Data is empty because probably there's no, yep. There's
Yeah,
an
we're not
empty
returning
response.
anything. Yeah, for people still listening in, then you can add a lot of extra information to this. We've only shown like a small subset of stuff. You can, handles can have responses to them, not only queries. You can also have logs in them, all sorts of stuff like that. You can have interactions between contracts. There's a lot of stuff we're not showing here today.
I think we'll end here. We can also maybe try and add a closing option. But I think this is enough for now. Right, guys?
Yeah, looks good.
Yeah, I think we've shown people the basics of how to interact with stuff.
With stuff.
with the network.
All right.
Yeah, I'm sure people would like to continue working on that. We have provided them the links. The replay of this workshop will be posted on the Cosmos YouTube channel. It will also be posted on the website under the Code with Us link. And it will live there forever in case people would like to go through the tutorial again. They'll be happy to. And in case people who have watched or people who will be watching have any questions for the team, just drop those in the Code Us workshop on channel on Discord, and I'll make sure to ping the team to address your questions if there will be any. So thank you so much, everyone, for joining. Thank you to Reuven, Tom, and Asaf for presenting an amazing workshop today. I hope everyone has enjoyed it, and I hope people will start using that tech that they have been building and could build some cool stuff going forward. Who knows? Drop them a message or a link if you have some cool, interesting ideas to work on, and let's see what comes out of this. Thank you so much, everyone.
Thank you for having us.
Yeah, thank you Allah for giving us this platform. We really appreciate it. And
we just posted a link to the presentation, and the last slide of the presentation contains a lot of links and interesting things you can check out. And yeah, sorry, Reuven, go ahead.
No, I'm just like while you're talking, I'm just showing people on screen. This is where you can find the code that we've been working on today. And just jump in here and you can check it out, the simple permissions branch of this repository.
Yeah, Tobias, if you are on, let's copy the link, add them to the message chat on Cosmos YouTube, and make sure if there are any questions, we'll make sure to ping you and address them as soon as possible. Thank you everyone for joining again. Hope you enjoyed it, and let's see each other on the next Code With Us workshop. Happy holidays.
Thank you very much. You too. Thank you.
Thank you.
Bye-bye.
Take care.
Bye-bye.
Bye.
All right, this live stream is now going to an end.